made up of atoms, the building blocks of the universe. But how did we understand these tiny, invisible particles? The journey of the atomic theory spans centuries and is filled with curiosity, experimentation, and groundbreaking discoveries. Let's dive into the minds of scientists prepared to ask big questions and change our view of the universe forever.
Fellow thinkers, I present to you a vision of the universe that is both simple and profound. Everything around us, all that we can touch, see, and experience, is composed of invisible, indestructible particles. I call these particles atoms from the Greek word atomos, meaning uncuttable or indivisible. I propose that there is not an infinite divisibility of matter, as some might suggest. Instead, at the smallest level, we find these atoms solid and indivisible, yet different in shape, size, and mass. These differences in form and structure account for the diversity of materials we observe. A stone is different from water not because they are made of fundamental different substances, but because the atoms that compose them are arranged differently and shaped distinctively.
Ernest Rutherford. In 1911, I transformed the understanding of atomic structure with my discovery of the nucleus. Through my gold foil experiment, I revealed that atoms have a tiny, dense, positively charged center, which I named the nucleus, with electrons moving around in it, mostly empty space. This led to the development of the nuclear model of the atom, replacing the older plum-pudding model. I also discovered the proton as a key particle in the nucleus. These breakthroughs were crucial in advancing modern atomic theory and opening the door to nuclear physics.
Hello, I am John Dalton. In 1803, I proposed the atomic theory which revolutionized chemistry. I discovered that all matter is made of tiny indivisible particles called atoms. Each element has its own unique atoms and they combine in fixed ratios to form compounds. My work on gases also led to the law of partial pressures, showing that each gas in a mixture acts independently. Using these ideas, I created the first table of atomic weights, giving us a clearer understanding of how atoms combine.
Niels Bohr planetary model, proposed in 1913, depicted the atom as a miniature solar system where electrons orbit the nucleus-defined paths. Similar to planet around the sun, this model introduced quantized energy levels explaining how electrons can jump between orbits by absorbing or emitting energy, thereby accounting for atomic stability and the emission spectra of elements like hydrogen. Bohr's planetary model marked a significant shift in atomic theory by integrating quantum concept with classical mechanics. He proposed that these electron orbits are stable and quantized, meaning electrons do not radiate energy while in a given orbit, which addressed the problem of atomic instability. These models explain the discrete spectral lines observed in hydrogen, laying the groundwork for future developments in quantum mechanics and enhancing our understanding of atomic structure.
Though Schrodinger's and Heisenberg's model may appear distinct, they are mathematically equivalent and represent different ways of describing the same quantum reality. Together, their theories form the foundation of modern quantum mechanics, replacing classical atomic models with a probabilistic and non-deterministic view of atomic structure. Heisenberg, on the other hand, developed matrix mechanics, a different approach to quantum mechanics, and introduced the Heisenberg uncertainty principle. This principle states that it is impossible to know both the exact position and momentum of an electron simultaneously, highlighting the limits of measurements in quantum systems. While Schrödinger focused on wave behavior, Heisenberg's theory showed that electrons do not have precise orbits, but exist in a probabilistic manner.
James Chadwick's discovery of neutrons in 1932 was a groundbreaking development in atomic theory. Before this, protons and electrons were believed to be the only components of atoms. Chadwick's experiment with beryllium showed that when we bombarded with alpha particles, an unknown radiation was released. He deduced that this was caused by neutral particles, which he named neutrons. This discovery helped and explained the stability of nucleus and led to advancement in nuclear physics, including the development of nuclear energy and atomic bomb.
Thanks for joining us on this journey through the fascinating world of atomic theory and the brilliant scientists who shaped our understanding of the atom, from Democritus's early ideas to the complex quantum models of today. Each discovery has brought us closer to understanding the building blocks of the universe. Until next time, keep exploring the wonders of the atom.